Every gold ring on your finger was forged in a collision, so violent it warped the fabric of space-time itself. And yet most people have no idea that this simple metal connects the birth of the universe to the modern economy in ways that are almost too strange to believe. Gold is not just expensive, it is not just shiny, and it is not just rare. Gold is a relic of cosmic catastrophe, a product of Einstein's relativity, and quite possibly the most extraordinary element on the periodic table. The question that drives everything forward is deceptively simple. Why does humanity lose its mind over a metal you cannot eat, cannot burn for fuel, and cannot use to build a house? The answer takes us from the interior of collapsing stars to the vaults beneath the Federal Reserve Bank of New York. From quantum physics to ancient trade routes, and from the behavior of electrons traveling near the speed of light to the reason your smartphone works every single morning. This is the story of gold, and once you understand it, you will never look at a piece of jewelry or a gold bar the same way again. Gold sits at position 79 on the periodic table, carrying the symbol O from the Latin word aurum. Its atomic nucleus contains 79 protons, and in its most common stable isotope, gold, 197, it also holds 118 neutrons. On the surface, this makes it seem like just another metallic element, one of dozens arranged neatly in the periodic table's transition metal block. But gold is not like the others. Consider what happens when you leave a piece of iron outside for a few months. Oxygen in the atmosphere bonds with the iron atoms, forming iron oxide, which we call rust. The metal flakes apart, turns reddish-brown, and eventually crumbles into dust. Silver tarnishes when exposed to sulfur compounds in the air, developing a dark coating of silver sulfide. Copper reacts with carbon dioxide and moisture to form a greenish layer called verdigris, which is why the Statue of Liberty, originally the color of a new penny, turned green over the decades. Aluminum forms a thin oxide layer almost instantly upon exposure to air. Zinc corrodes. Virtually every common metal you can think of deteriorates when left to the mercy of the natural environment. Gold does not. You can bury a gold coin in wet soil for 1,000 years, dig it up, rinse it off, and it will look almost exactly the same as the day it was buried. You can submerge gold in seawater, expose it to acid rain, leave it in a tropical jungle, or blast it with ultraviolet radiation, and it remains fundamentally unchanged. This is not a minor curiosity. This single property, the near-total chemical inertness of gold, is one of the primary reasons human civilization chose this particular metal as the universal store of value. But why is gold so stubbornly unreactive? The answer lies in its electron configuration, and specifically in how those electrons behave at the quantum mechanical level. Gold's outermost electron, the one that would typically participate in chemical bonding with other elements, is held unusually tightly to the nucleus. In most metals, outer electrons are relatively free to interact with neighboring atoms, which is why those metals corrode so readily. Gold's electron, however, is pulled inward by the enormous positive charge of its 79-proton nucleus. The electrons closest to the nucleus are moving at velocities that approach a significant fraction of the speed of light, according to Einstein's special theory of relativity. When any object with mass moves at speeds approaching the speed of light, its relativistic mass increases. This is not a metaphor or an approximation. It is a measurable physical effect. For gold's inner electrons, this relativistic mass increase causes their orbitals to contract inward, pulling closer to the nucleus. This contraction has a cascading effect on the outer electrons as well, stabilizing them and making them far less willing to participate in chemical reactions. The technical term for this is relativistic contraction of the s orbitals, and it is the reason gold refuses to rust, tarnish, or corrode under normal conditions. Without Einstein's relativity, gold would behave much more like silver or copper. It would react with air and water. It would tarnish. It would lose its luster over time. The fact that gold maintains its beauty and integrity across millennia is directly attributable to the laws of physics operating at the subatomic level. This is a profound realization. The metal that humans have worshipped, fought wars over, and used as currency for thousands of years owes its most prized quality, its permanence, to the same physics that governs black holes and the bending of light around massive objects. This brings us to perhaps the most visually striking property of gold, its color. Think about metals for a moment. Iron is silvery gray. Aluminum is silvery white. Platinum is silvery. Nickel is silvery. Chromium is silvery. Silver itself is, obviously, silver. The vast majority of metals reflect visible light more or less equally across all wavelengths, which is why they appear silver or gray to our eyes. Gold breaks this pattern completely. It reflects a warm, yellowish light that humans have found beautiful for as long as recorded history exists. The reason gold has this distinctive color is, once again, relativistic. In most metals, the energy gap between the electron orbitals that absorb and emit light is large enough that only ultraviolet photons, which are invisible to the human eye, get absorbed. Visible light bounces off equally, producing a silver appearance. In gold, the relativistic contraction of the inner orbitals and the corresponding expansion of the outer d orbitals reduce the energy gap to a point where blue light, which has a relatively short wavelength and high energy within the visible spectrum, gets absorbed. When blue light is removed from the reflected spectrum, what remains is a combination of red, orange, and yellow wavelengths. This is what we perceive as gold's characteristic warm, yellow color. If you could somehow turn off relativistic effects while keeping everything else about gold's atomic structure the same, gold would look silver. The color that has mesmerized pharaohs, emperors, conquistadors, and modern investors alike is a direct visual manifestation of Einstein's special relativity operating at the atomic scale. This is not speculation or theoretical musing. It is established physics, confirmed by relativistic quantum chemistry calculations that accurately predict gold's optical properties only when relativistic corrections are included. Remove those corrections, and the calculations predict a silver-colored metal. Include them, and you get the golden hue that has shaped human history. In a very real sense, the beauty that made gold valuable to ancient civilizations was painted by the laws of the universe themselves. Now we arrive at what might be the most astonishing part of gold's story, where it actually comes from. Gold is not manufactured on Earth. It cannot be. No chemical reaction, no industrial process, no amount of heat or pressure available on our planet can transmute other elements into gold. This is not a technological limitation that future science might overcome. It is a fundamental constraint of nuclear physics. Creating gold requires building an atomic nucleus with exactly 79 protons, and doing so requires nuclear reactions of extraordinary violence. For decades, astrophysicists assumed that gold and other heavy elements were produced primarily in supernova explosions, the catastrophic detonations that occur when massive stars exhaust their nuclear fuel and collapse. Supernovae are indeed among the most energetic events in the universe. A single supernova can briefly outshine an entire galaxy of hundreds of billions of stars. The temperatures and pressures generated in these explosions are extreme enough to forge elements heavier than iron through a process called neutron capture, where atomic nuclei absorb free neutrons and then undergo beta decay to increase their proton count. However, as computational models improved and observational data accumulated, a problem emerged. Supernovae alone could not account for the quantities of the heaviest elements, including gold, observed in the universe. The neutron flux in a typical supernova, while enormous by terrestrial standards, appeared insufficient to produce adequate amounts of elements at gold's mass range through what physicists call the R process, or rapid neutron capture process. The R process requires an environment so flooded with free neutrons that atomic nuclei can capture them faster than they can decay, building up to very heavy masses before the process stops. Something even more extreme than a supernova was needed. That something turned out to be neutron-star mergers. A neutron star is what remains after a massive star goes supernova. When the core of a star between roughly 8 and 25 solar masses collapses, the protons and electrons are crushed together by gravity to form neutrons, creating an object of almost incomprehensible density. A typical neutron star packs about 1.5 times the mass of our Sun into a sphere roughly 12 miles across. A teaspoon of neutron star material would weigh approximately 6 billion tons on Earth. These objects are essentially city-sized atomic nuclei, held together by gravity, so intense that their surfaces have escape velocities around one-third the speed of light. When two neutron stars orbit each other in a binary system, they gradually lose energy by emitting gravitational waves. Ripples in the fabric of space-time predicted by Einstein's general theory of relativity. Over millions or billions of years, this energy loss causes the two stars to spiral inward toward each other, orbiting faster and faster until they finally collide and merge. The collision of two neutron stars is among the most violent events in the known universe. In the final milliseconds before merger, the stars are orbiting each other hundreds of times per second. When they make contact, the resulting explosion, called a kilonova, releases more energy in a fraction of a second than our Sun will produce in its entire 10 billion year lifetime. The temperatures reach hundreds of billions of degrees. The gravitational waves generated are strong enough to be detected by instruments on Earth, over 100 million light-years away. And critically, the merger ejects enormous quantities of neutron-rich material into space at significant fractions of the speed of light. This ejected material is the birthplace of gold. In the expanding cloud of neutron-rich debris, conditions are finally extreme enough for the R process to operate efficiently. Atomic nuclei are bombarded with neutrons at rates so high that they can capture dozens of neutrons before having time to decay, building up to masses corresponding to gold, platinum, uranium, and other heavy elements. Within seconds to minutes of the merger, the radioactive decay of these newly formed elements powers the kilonova's visible light, producing a distinctive glow that transitions from blue to red over the course of days as different elements decay. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected a signal designated GW 170817, which matched the theoretical prediction for two merging neutron stars. Within seconds, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. Over the following days and weeks, telescopes around the world and in orbit observed the kilonova associated with this merger. Located in the galaxy NGC 4993, approximately 130 million light-years from Earth. The spectroscopic analysis of this kilonova provided the first direct observational evidence that neutron-star mergers produce heavy R-process elements. Researchers identified signatures consistent with the production of elements including gold, platinum, and other precious metals. The amount of gold estimated to have been produced in this single merger event was staggering. Approximately 10 Earth masses worth of gold, or roughly 10 times the mass of our entire planet converted into this one element alone. Published research from teams at institutions including MIT, Caltech, and the University of California estimated that neutron-star mergers across cosmic history can account for most or all of the gold present in the universe today. This means that every atom of gold on Earth, every atom in your jewelry, in the circuits of your phone, in the vaults of Fort Knox, in the reserves held by the United States Federal Reserve, was created in one or more neutron-star collisions that occurred billions of years ago, long before our solar system even existed. The gold atoms were scattered into the interstellar medium, mixed with hydrogen and other elements in molecular clouds, and eventually incorporated into the disk of gas and dust that collapsed to form our Sun and planets approximately 4.5 billion years ago. During Earth's formation, most of the gold sank toward the planet's core along with other heavy elements, pulled inward by gravity during the period of planetary differentiation, when Earth was still largely molten. The gold that we find near the surface today is believed to have been delivered later, during a period called the Late Heavy Bombardment, roughly 4 billion years ago, when asteroids and meteorites rich in heavy elements pelted the young Earth and deposited their metallic cargo in the crust and upper mantle. So when you hold a gold coin in your hand, you are holding material that was forged in the collision of dead stars, scattered across light-years of space, incorporated into a cloud of gas that became our solar system, sank to the core of a molten planet, and was then redelivered to the surface by asteroid impacts. The journey from neutron-star merger to your palm spans billions of years and billions of light-years. There is perhaps no other everyday material with such an extraordinary origin story. Understanding where gold comes from helps explain another of its critical properties, its rarity. Gold is scarce precisely because its formation requires an event, neutron star mergers, that is itself extraordinarily rare. In a galaxy the size of the Milky Way, neutron star mergers are estimated to occur only once every 10,000 to 100,000 years. Each merger produces a finite amount of heavy elements, and that material must then disperse across vast distances to be incorporated into new star systems. The result is that gold makes up only about 4 parts per billion of Earth's crust by mass. To put this in perspective, for every billion atoms in Earth's crust, only about 4 are gold. This translates to extremely low concentrations in most rock, typically just a few grams per ton of, or at commercially viable gold mines. The total amount of gold ever mined in all of human history is estimated at approximately 220,000 metric tons as of recent years, according to data compiled by the World Gold Council and various mining industry analyses. This sounds like a lot until you realize that if you melted all of it down and cast it into a single cube, that cube would measure only about 22 meters on each side, roughly fitting within a single tennis court. All the gold that all of humanity has ever extracted from the earth across thousands of years of mining would form a cube smaller than a typical American house. This scarcity is not artificial. It is cosmic. Gold is rare because the universe does not make very much of it, and what it does make is spread incredibly thinly across the vastness of space. One of gold's most remarkable economic properties follows directly from its physical indestructibility. Gold accumulates. It is never consumed in the way that oil is consumed, or food is consumed, or even in the way that industrial metals like copper and aluminum are consumed. When you burn gasoline, the hydrocarbons break apart and recombine with oxygen to form carbon dioxide and water, dispersing irretrievably into the atmosphere. When iron rusts, it gradually loses structural integrity and eventually returns to the earth as iron oxide. When food is eaten, it is metabolized and its chemical bonds are broken to release energy. But when gold is used, it simply changes shape. A gold coin melted down becomes a gold bar. A gold bar worked by a jeweler becomes a necklace. A necklace discarded and recycled becomes the gold plating on a circuit board. The gold atoms themselves are never destroyed, never decomposed, never dispersed beyond recovery in any typical use case. This means that virtually every ounce of gold ever mined in human history still exists in recoverable form somewhere on Earth. According to estimates from the World Gold Council and consulting firms like Boston Consulting Group, the above-ground stock of gold has only grown over time. None has been lost to chemical decay. Some relatively small amounts have been effectively lost, sunk in shipwrecks at the bottom of the ocean, scattered in electronic waste in landfills, or dispersed in extremely thin coatings that are uneconomical to recover. But the vast majority remains in circulation as bullion, coins, jewelry, or industrial components. This property of accumulation rather than consumption is unique among major commodities and is central to gold's monetary role. Economists refer to gold's stock-to-flow ratio, the ratio of existing above-ground gold to the amount newly mined each year, as exceptionally high. Current annual gold mine production is roughly 3,000 to 3,500 metric tons per year, while the total above-ground stock exceeds 200,000 metric tons. This means it would take more than 60 years of mining at current rates to double the existing supply. No other commodity has this characteristic to the same degree. Oil is consumed and must be continuously extracted. Agricultural products are consumed within months. Even silver, gold's closest analog, is consumed in significant quantities by industry in ways that are often unrecoverable. Gold simply persists. This persistence means that the gold in a ring purchased today might contain atoms that were once part of a coin minted during the Roman Republic, melted down during the fall of Rome, recast into Byzantine jewelry, seized during the Crusades, melted again and shipped across the Atlantic by Spanish conquistadors, minted into American coinage, stored in the vaults at Fort Knox, and eventually sold to a jeweler in New York who fashioned it into the ring on your finger. The same atoms, the same 79 protons in each nucleus. Unchanged across 2,000 years of human drama. This is not poetic license. It is physical fact. Gold is eternal in a way that almost nothing else in human experience is eternal. The question of why gold became money is one that economists and historians have debated extensively. But when you understand gold's physical properties, the answer becomes almost inevitable. For any substance to function as money, it needs to satisfy several criteria simultaneously. It must be durable, meaning it does not rot, rust, evaporate, or decompose. It must be divisible, meaning it can be split into smaller pieces without losing its essential character. It must be portable, meaning high value can be stored in a small, lightweight form. It must be fungible, meaning one unit is interchangeable with any other unit of the same weight. It must be recognizable, meaning people can readily identify it and distinguish it from counterfeits. And it must be scarce, meaning its supply cannot be easily inflated by anyone who wants more of it. Run through the periodic table with these criteria in mind, and an extraordinary process of elimination occurs. Gases are immediately excluded, because you cannot carry them around conveniently as currency. Liquids at room temperature are limited to mercury and bromine, both of which are toxic and impractical. Radioactive elements are excluded for obvious safety reasons, eliminating everything past bismuth on the periodic table, as well as elements like radium and uranium. Highly reactive metals like sodium, potassium, and cesium are excluded because they react violently with water or air. Metals that corrode readily, including iron, copper, lead, zinc, and nickel, fail the durability test. Rare earth elements, despite their name, are actually fairly abundant but are difficult to distinguish from one another and hard to refine. Aluminum, while resistant to deep corrosion, was historically extremely difficult to extract from or was once more valuable than gold in the early 19th century, but became dirt cheap once industrial smelting was developed, making its supply too easily inflated. Platinum and palladium are chemically stable and rare, but they have melting points so high. Platinum melts at over 3,100 degrees Fahrenheit that ancient civilizations could not work them. You cannot mint coins from a metal you cannot melt with available technology. Silver comes close to gold in many respects, and indeed served as money alongside gold for most of history. However, silver tarnishes when exposed to sulfur compounds, is more abundant than gold, which means larger quantities are needed to represent the same value, making it less portable for large transactions, and historically saw its value fluctuate more dramatically as large new deposits were discovered. Gold threads the needle perfectly. It melts at 1,948 degrees Fahrenheit, well within the reach of ancient furnace technology. It is soft enough to stamp into coins, yet hard enough to resist excessive wear in circulation. It is dense, 19.3 grams per cubic centimeter, meaning significant value can be packed into a small volume. And this density also makes it extremely difficult to counterfeit because few other materials match gold's specific gravity. A lead core covered in gold plating, a common counterfeiting technique through history, can be detected simply by weighing the coin and measuring its volume, since lead is less dense than gold. Gold is scarce enough that its supply grows only slowly, preventing inflation, yet abundant enough that sufficient quantities exist to support an economy. And of course, gold does not corrode, ensuring that coins retain their weight and purity indefinitely. The ancient kingdom of Lydia in what is now Western Turkey is generally credited with producing the first standardized gold coins around 600 BCE. But gold had functioned as money in less standardized forms, weighed gold dust, gold rings, gold bars for thousands of years before that. The choice of gold was not arbitrary cultural preference. It was the inevitable result of physical law eliminating all other candidates. In a very real sense, the laws of physics chose gold as money long before any human king stamped his face on a coin. Gold's role in the modern economy remains enormous. Despite the fact that the world abandoned the gold standard in stages during the 20th century, with the United States fully severing the dollar's tie to gold in 1971 under President Nixon. Today, no major national currency is directly backed by gold. Money creation is managed by central banks through monetary policy. and currencies float against each other on foreign exchange markets based on economic fundamentals, interest rates, and market sentiment. Yet gold has not become irrelevant. Far from it. Central banks around the world collectively hold more than 35,000 metric tons of gold in their reserves. The United States alone holds approximately 8,133 metric tons in facilities, including Fort Knox in Kentucky, the Federal Reserve Bank of New York, and the Denver and Philadelphia mints, making it by far the largest official gold holder in the world. This gold is valued on the Federal Reserve's balance sheet and serves as a foundation of confidence in the financial system, even though the dollar is no longer directly convertible to gold. Germany holds approximately 3,350 metric tons, Italy about 2,450, France about 2,435, and Russia and China have been aggressively increasing their holdings in recent years. The fact that these nations continue to acquire and hold gold tells you something important about how the global financial system truly operates beneath its surface of fiat currencies and digital transactions. Gold serves as the ultimate hedge against systemic risk. When stock markets crash, when currencies collapse, when governments default on their debt, when geopolitical conflict erupts, gold typically rises in value because it is the one financial asset that carries no counterparty risk. A government bond is only as good as the government behind it. A bank deposit is only as safe as the bank holding it. A stock is only as valuable as the company issuing it. But gold is gold. Its value depends on no one's promise, no institution's solvency, no government's fiscal discipline. This is why, during the 2008 financial crisis, gold prices surged from around $800 per ounce to over $1,900 per ounce by 2011 as investors fled paper assets for the security of physical metal. It is why, during periods of high inflation, gold historically maintains purchasing power while currencies lose theirs. A single ounce of gold in ancient Rome could buy a fine toga, belt, and pair of sandals, an outfit suitable for a gentleman. Today, a single ounce of gold, valued at over $2,000 at recent prices, can still buy a respectable suit, belt, and pair of shoes. Across 2,000 years of monetary upheaval, empire collapse, hyperinflation, and economic revolution, gold has maintained approximately the same purchasing power in terms of basic goods. No fiat currency has ever achieved this kind of long-term stability. The longest surviving paper currency in continuous use, the British pound sterling, has lost over 99% of its purchasing power since its inception. The US dollar has lost approximately 97% of its purchasing power since the Federal Reserve was created in 1913. Gold, by contrast, simply endures. But gold is not merely a financial instrument or a store of value. In the 21st century, gold has become an indispensable industrial material, critical to technologies that define modern life. Consider the electronics in your pocket. Every smartphone contains a small but essential amount of gold. The connectors that link your phone's components together are gold-plated because gold provides a reliable, corrosion-resistant electrical contact. The wire bonds inside semiconductor chips, the microscopic wires that connect the silicon die to the chip's external pins, are often made of gold because gold bonds reliably to both silicon and the package materials. Data center servers, the backbone of the internet, rely on gold-plated connectors for reliable high-speed data transmission. A typical smartphone contains approximately 30 milligrams of gold, which sounds trivial until you consider that over 1.4 billion smartphones are sold annually worldwide. That amounts to roughly 42 metric tons of gold consumed by the smartphone industry alone each year. Add in computers, tablets, televisions, automotive electronics, industrial control systems, medical devices, military hardware, and telecommunications equipment, and the electronics industry consumes approximately 300 metric tons of gold annually, making it one of the largest industrial consumers of the metal. In medicine, gold has moved far beyond the ornamental. Gold nanoparticles, particles measuring just a few nanometers in diameter, have emerged as one of the most promising platforms in modern biomedical research. These particles can be engineered to accumulate preferentially in tumor tissue due to a phenomenon called the enhanced permeability and retention effect, where the leaky blood vessels surrounding tumors allow nanoparticles to pass through and accumulate. Once concentrated in the tumor, gold nanoparticles can be activated by near-infrared laser light, causing them to heat up and destroy the surrounding cancer cells in a technique called photothermal therapy. Clinical trials are underway at major American research hospitals exploring this approach for various cancer types. Gold nanoparticles are also being developed as drug delivery vehicles, carrying chemotherapy agents directly to tumors and releasing them on command, reducing side effects by limiting exposure of healthy tissue to toxic drugs. In diagnostic medicine, gold nanoparticles are already widely used. The rapid COVID-19 lateral flow tests that became ubiquitous during the pandemic rely on gold nanoparticles to produce the colored line that indicates a positive result. Gold compounds have been used in the treatment of rheumatoid arthritis for decades, a practice called chrysotherapy, and research continues into gold-based drugs for other inflammatory and autoimmune conditions. The biocompatibility of gold, its refusal to react with bodily fluids or trigger immune responses, makes it uniquely suited for medical implants and devices that must remain in the body for extended periods. In aerospace and space exploration, gold plays roles that no other material can fill. The James Webb Space Telescope, launched by NASA on December 25, 2021, and now stationed at the second Lagrange point roughly 1 million miles from Earth, observes the universe primarily in infrared light. Its primary mirror, measuring 21 feet 4 inches across and composed of 18 hexagonal beryllium segments, is coated with a thin layer of gold just 100 nanometers thick, approximately 1,000 atoms deep. Gold was chosen because it reflects over 98% of infrared light, making it the ideal coating for an infrared telescope's mirrors. The total amount of gold used on the Webb telescope's mirrors is approximately 48 grams, less than 2 ounces. Yet this vanishingly thin layer is what allows humanity to peer deeper into the universe than ever before, capturing images of galaxies as they appeared over 13 billion years ago. Astronaut helmet visors incorporate a thin gold coating that reflects harmful solar radiation while remaining transparent enough to see through. Without this gold layer, astronauts conducting spacewalks would risk severe eye damage from unfiltered solar ultraviolet and infrared radiation. Spacecraft electronics, satellites, and space station components all rely extensively on gold plating for reliable electrical connections in the vacuum of space, where corrosion by atomic oxygen and extreme temperature cycling would destroy less noble metals. Gold's extraordinary density, combined with its malleability and resistance to corrosion, also makes it valuable in specialized radiation shielding applications. Gold's high atomic number means it is effective at absorbing X-rays and gamma rays, and gold foil is used in certain medical radiation therapy applications to shape radiation beams with high precision. In particle physics, gold nuclei are accelerated to near-light speeds and smashed together at facilities like the relativistic heavy ion collider at Brookhaven National Laboratory in New York to recreate conditions that existed microseconds after the Big Bang, producing a state of matter called quark-gluon plasma. Gold is used in these experiments precisely because its large, heavy nucleus produces the most energetic collisions and the highest densities of nuclear matter. The gold market itself is a fascinating economic ecosystem. The global gold market is enormous, with daily trading volumes in London alone, the world's largest gold trading center, averaging tens of billions of dollars. The price of gold is determined through continuous trading on exchanges, including the COMEX division of the New York Mercantile Exchange, the London Bullion Market, and the Shanghai Gold Exchange. Gold futures contracts allow investors, miners, jewelry companies, and speculators to buy and sell gold at agreed-upon future dates and prices, creating a liquid and efficient market. Gold exchange-traded funds, or ETFs, have made gold investment accessible to ordinary Americans who might not want to physically store gold bars. The SBDR Gold Shares ETF, ticker symbol GLD, launched in 2004, holds over 900 metric tons of physical gold in vaults on behalf of its shareholders, making it one of the largest gold holders in the world. larger than the official reserves of all but a handful of nations. The gold mining industry itself employs hundreds of thousands of people worldwide. The United States has significant gold mining operations, primarily in Nevada, which produces more gold than any other state, with the Carlin Trend and associated deposits representing one of the world's richest gold-producing regions. American gold production amounts to roughly 170 to 200 metric tons annually, making the United States one of the top 5 gold-producing nations. Globally, the largest gold producers include China, Australia, Russia, Canada, and the United States, with total world mine production typically ranging between 3,000 and 3,500 metric tons per year. The environmental impact of gold mining is substantial and worth acknowledging. Extracting gold from ore requires moving enormous quantities of rock. Because gold concentrations are so low, typically just a few grams per ton of, or in commercial mines, producing a single ounce of gold requires processing approximately 20 to 30 tons of rock. This creates vast open-pit mines, enormous waste rock piles, and tailings ponds containing the chemical residues of extraction processes. Many gold mines use cyanide heap leaching, where dilute cyanide solutions are sprayed over crushed or to dissolve the gold, which is then recovered from the solution. While modern mines in the United States and other developed nations operate under strict environmental regulations, the history of gold mining is littered with environmental disasters. From mercury contamination during the California Gold Rush of 1849 to cyanide spills in various countries in recent decades. The energy consumption of gold mining is also significant, with estimates suggesting that producing 1 ounce of gold requires roughly the same amount of electricity as powering an average American home for 10 days. These environmental costs are part of gold's full story and add another dimension to its value. The immense human and environmental effort required to bring each ounce from deep underground into human hands. The psychology of gold is equally fascinating. Behavioral economists and evolutionary psychologists have proposed various explanations for humanity's deep attraction to gold. Some researchers suggest that the golden color triggers positive neurological responses because it resembles sunlight, ripe fruit, and warm fire, all of which are associated with survival advantages in our evolutionary past. Others point to gold's resistance to tarnishing as creating a subconscious association with immortality and permanence, qualities that humans universally desire but can never achieve for themselves. Gold has been found in burial sites dating back over 6,000 years, suggesting that even the earliest complex human societies associated gold with transcendence, with something that endures beyond death. The fact that gold is dense and heavy when held in the hand may also contribute to its psychological impact, creating a tactile sense of substance and value that lighter materials lack. Whatever the precise psychological mechanisms, the human response to gold appears remarkably consistent across cultures and time periods. Civilizations that had no contact with each other, separated by oceans and millennia, independently arrived at the conclusion that gold was supremely valuable. This universality suggests that the attraction is not merely cultural but rooted in something deeper, perhaps in the very physical properties that make gold unique among the elements. Let us consider what all of this means when taken together. Gold is an element whose color is determined by Einstein's special relativity. Its existence required the collision of neutron stars in events of almost inconceivable violence, billions of years before Earth formed. Its chemical stability arises from quantum mechanical properties of its electron structure. Its scarcity reflects the rarity of the cosmic events that create it. Its permanence makes it the only material that truly accumulates across all of human history without degradation. Its physical properties made it the inevitable choice for money among all the elements on the periodic table. Its role in the modern economy remains vital both as a financial safe haven and as an industrial material critical to electronics, medicine, and space exploration. No other element combines all of these qualities. No other substance can claim to be simultaneously a product of relativistic physics, neutron star alchemy, evolutionary psychology, economic theory, and cutting-edge nanotechnology. Gold stands at the intersection of cosmology, quantum mechanics, chemistry, economics, and human civilization in a way that is genuinely unique in the natural world. The final insight that emerges from understanding gold is perhaps the most humbling. The gold that exists on Earth today represents a finite inheritance from the universe. No new gold is being created in our solar system. The last neutron star merger that contributed gold to what would become our solar system occurred billions of years ago, before the sun even ignited. We are spending a cosmic inheritance, atom by atom, ring by ring, circuit board by circuit board. The total amount available to humanity is fixed by events that occurred in deep space before our planet existed. When we mine gold, we are not manufacturing anything. We are merely relocating atoms from underground to above ground, taking what the universe deposited here billions of years ago and moving it into human hands. This gives gold a metaphysical significance that transcends its market price. Every gold atom is a messenger from the distant past, carrying within it 79 protons and 118 neutrons, the signature of a cosmic cataclysm that occurred when the universe was younger, when our galaxy was still assembling itself from primordial gas clouds, when the Earth itself was nothing more than a possibility encoded in the composition of a molecular cloud drifting through interstellar space. When you look at gold and see its warm yellow glow, you are seeing the color that relativity painted on an element forged in the most violent explosions the universe has ever produced, delivered to Earth by asteroids, extracted from rock by human ingenuity, and shaped by human hands into objects of beauty and utility. You are seeing billions of years of cosmic history compressed into a single gleaming surface. That is what gold truly is. Not just a metal, not just money, not just jewelry. Gold is a story written in protons and neutrons, authored by colliding stars, illustrated by quantum mechanics, and read by every civilization that has ever held it in wonder. It is the universe's autobiography, told in 79 protons at a time. And it has been telling that story long before humans existed to listen. And it will continue telling it long after we are gone.